Hi, today's lesson is solving equations with radicals. Equations with radicals are equations that contain radical expressions. For example, the square root of x minus 4 equals 8, or the square root of 5x plus 12 is equal to the square root of 2x minus 1. Our goal in solving these equations is the same as any type of equation that we solve. We want to try to isolate the variable to one side of the equation to get x equals some number. Well, the thing you have to do here first is get the x outside of the radical. And so the key is to remove the radical. And do you remember we talked about this property in an earlier section? If we square the square root of p, where the square root of p is defined as a real number, do you remember what happens to that? Yeah, squaring the square root just removes the radical sign, and we get what is inside. And so that's going to be our key to solving these radical equations, that is to square the radical. And then you have to remember the rule that what you do to one side, you have to do to the other side of the equation. So let's look at the steps that we have to go through to solve radical equations. The first thing we need to do is to isolate the radical expression to one side of the equation. If the equation contains two radical expressions, we want one radical on each side of the equation. Then we're going to apply the power rule, that power rule being that we will raise both sides to the power of the index to eliminate the radical. Now, I just illustrated on the last screen with the square root. If we square a square root, we remove the radical. If you happen to have a cube root in your equation, you would have to raise it to the third power. So remember what the index is. That is that number that tells you what root you're taking. So you just want to raise both sides to that power. And then you're going to solve the resulting equation, which will happen to be either linear or quadratic. And then most important in this type of problem is that you have to check all solutions in the original equation. Since we alter the original form of the equation, some of the solutions that we get may not actually work in that original, so we have to go back and check those. So let's start looking at some examples to get you comfortable with this. So if we have the square root of r minus 2 is equal to 3, what we would do here, since we have the radical expression already isolated, we would have to raise both sides to the power of the index, which in this case is a 2. And in doing, squaring the square root of r minus 2 just gives us r minus 2 is equal to 9. Now we can add 2 to both sides to get r is equal to 11. Now we have to check. We plug in 11 in place of r inside the original equation. The square root of 11 minus 2, is that equal to the value of 3? And yes, 11 minus 2 is 9, and the square root of 9 is 3. So our solution to this equation is the value 11. Now the second example, the square root of 7m minus 3 is equal to 5. Very similar to the first problem, we're just going to square both sides. And in so doing, we get just 7m minus 3 is equal to 25. So we add 3 to both sides to get 7m is equal to 28. And then divide both sides by 7 to get m is equal to 4. So checking this in our original equation, we have is 7 times 4 minus 3 in the square root equal to 5. And that is true. That's 28 minus 3, which gives us 25. And the square root of 25 is 5. So the value 4 is the solution to this equation. Oops. Okay. So far, so good. Let's look at an example where we have to do some work to the equation. This is the square root of 5k minus 3 plus 2 equals 0. So before we can square, we have to isolate this radical expression. So that means we need to remove the 2. We can remove the 2 by subtracting 2 from both sides. So we would get the square root of 5k minus 3 is equal to negative 2. Now at this point, we can square both sides. And squaring the square root of 5k minus 3 just eliminates the radical. Squaring a negative 2 gives us positive 4. So we would add 3 to both sides to get 5k is equal to 7, and divide by 5, so k is 7/5. Now, we have to check our work, and so whenever we check, we have to go back to the original equation and plug in the value for k that we found, which is 7/5. Okay, make sure you understand what is in the radical and what is not. That plus 2 is not in the radical, so we have to simplify this radical expression first. 5 times 7/5 is just 7 minus 3, so that's the square root of 4, plus 2. Does this equal 0? Well, the square root of 4 is 2, plus 2 does not equal 0, right? That gives us 4 equals 0, which is false. So what does that mean? That means that this 7/5 is actually not a solution to the original equation. This is the only possible solution, so since it doesn't work, there are no solutions to this equation. Now, why did that happen? Notice that 7/5 actually does solve this linear equation that resulted whenever we cleared the radical, but it doesn't work in the original. And that is because when we isolated the radical, notice that we had the square root of 5k minus 3 was equal to a negative 2, but the square root symbol denotes the principal or the positive root, and so we can never have a square root equal to a negative number. So that's kind of why we got the answer that we did here. Well, not kind of, it is the reason that we got the answer here. So anytime through that process of isolation, you get the square root equal to negative, you can kind of already conclude that there's going to be no solution to that. But here again, that's why it's important to check. I can bet on a final exam, you're going to have that 7/5 as an option for you to select. So if you don't know the true process to solve it, you would miss that problem. Now here's one more we have to isolate. We have the square root of 3k plus 1 minus 4 equals 0. So if we add 4 to both sides, we would get the square root of 3k plus 1 is equal to 4. Now notice this is a positive number that's equal to, so there's probably going to be a solution. So we have to, square both sides. So we would get 3k plus 1 is equal to 16. Subtract 1 from both sides. So 3k is equal to 15. And divide by 3. So k is 5. Now to check, the square root of 3 times 5 plus 1 minus 4, is that equal to 0? Well, 3 times 5 is 15 plus 1, which is 16. So this is the square root of 16 minus 4. Does that equal 0? And yeah, that's true because that's 4 minus 4, which is 0. So that checks. So the value 5 is the one that works for this equation. Now, let's look at one that has two radicals, but it's already in the form we need because I mentioned earlier the steps to solve. If you have a radical on each side, that is considered in the form we need it. So what we would do here is just square both sides of the equation. So we would square the 4p minus 2. Square the square root of 4p minus 2 and square the square root of 3p plus 5. And in so doing, we just get 4p minus 2 is equal to 3p plus 5. This is a linear equation, so to solve it, we're going to have to subtract 3p. And then if you want to go ahead and do this in this step, we can add 2 to both sides as well. So we would get p is equal to 7. So to check, is the square root of 4 times 7 minus 2 equal to the square root of 3 times 7 plus 5. So this is 28 minus 2, which is the square root of 26. This is 21 plus 5, which is the square root of 6. So yes, both sides are equal. So the value of 7 does satisfy the equation. Another one with two radicals. Again, this is considered to be isolated because we have a multiplication here. So we would square both sides. And on the left, you have to remember that when you're squaring a product, you have to square each of the factors inside. So we'd have to square the 2 to get 4. Square the square root of m just gives us m, and that's equal to 5m minus 16. So we can subtract 5m from both sides to get negative m is equal to, be careful here, that's a negative 16. So divide by negative 1 to give us m is equal to positive 16. So our check, we're looking at, does 2 times the square root of 16 give us the same thing as 5, the square root of 5 times 16 minus 16. So this is 2 times 4, oops, which is equal to 8. This is what? 5 times 16 is 80 minus 16, which is really the square root of 64, which is 8, so that checks. 16 is the solution that we need. Okay. Here's one that has a hideous looking problem, really. P is equal to the square root of p squared minus 3p plus 18. It might look kind of overwhelming to you, but the same process applies. We have a radical. The radical is isolated to one side, so we square both sides of the equation. But the nice thing that will happen, now on the left we just get p squared, but on the right it doesn't matter what is inside the radical, right? When we square it, we eliminate the radical, so don't worry about like multiplying p squared minus 3p plus 18 by itself, because it's inside the radical, so squaring just gives us that expression. Now notice this are p squared on both sides. We'd have to get the variables all on one side. But whenever we do that, we get 0 is equal to negative 3p plus 18. So when you have the same term on each side, they actually cancel out. We can add 3p to both sides. So we get 3p is equal to 18. And so therefore p is equal to 6 when we divide by 3. Now does this check? So to check, we're looking at, does 6 equal the square root of 6 squared minus 3 times 6 plus 18. Well, that would be 6 is equal to the square root of 36 minus 18 plus 18, which are eliminated. So we really get 6 equals the square root of 36, which is a true statement. So our solution is 6. Okay. Couple more examples and then we'll be done with this. The square root of 5 minus x is equal to x plus 1. That I have a lot of mistakes made on just because of some things we're going to see in this problem. But it is a radical equation. The radical is already isolated, so we need to square both sides of the equation. Now, squaring the radical, no problem, right? That's just 5 minus x. This is where the problems occur. Squaring a binomial, right? That's squaring x plus 1, which is x plus 1 times itself. When you square a binomial, you always get a trinomial. You can FOIL it out or you can use a pattern, but you square the first term is x squared. You double the product, so the product of those is x, doubled is 2x, and square the last, which is 1. Or multiply x plus 1 by x plus 1 using the FOIL method and you'll get the same thing. But I have a lot of mistakes there with students just putting x squared plus 1, right? When you have a sum, you can't just square each term. So this is a quadratic equation that we have to set equal to 0 and solve by factoring. So we would need to subtract 5 and add x to both sides. And that's going to give us 0 is equal to x squared plus 3x minus 4. And remember, to factor this trinomial, we have to look for the factors of 4, whose difference is 3, which would be 4 and 1. The last sign being negative tells us the signs of the binomial factors are different, and the larger one is positive. So we have x plus 4 and x minus 1. Then we set those factors to 0. So our two possible solutions here are negative 4 and 1. Now, if you're in a hurry, you would say both of those are the right answer, but let me show you that when we check, we actually find out one of them doesn't work. Now, you actually could get an equation where both of these work, or either neither work. It just depends on the equation that you have. But if I plug in, my equation was the square root of 5 minus x, so the square root of 5 minus negative 4 is equal to x plus 1. So that was negative 4 plus 1. Let me just make sure I had that right. Yes. So we get the square root of 5 plus 4, which is really the square root of 9. Then that square root of 9 is 3. Value of negative 4 does not work. Okay. What about x equals 1? If I plug in 5 minus 1, does that equal 1 plus 1? That's the square root of 4, which does equal 2. So that checks. So the only solution to this equation is the value 1. Now let me show you this graphically. Do you remember we talked about solving systems of equations back in an earlier chapter? And if you look at where they intersect, that is where solutions occur. So I'm going to go to the calculator, and let's enter our two sides of y1 and y2. So I'm going to press y equals, and in y1 I'm going to put in the square root minus x, close parentheses, and enter. The other side of my equation was x plus 1. And then I'm going to graph. This half-shaped parabola, which we'll talk about later on, is the square root of x. This is the line x plus 1, which you should understand how to. But they only cross at one point. And what is that x value where they cross? It is 1. So 1 is our only solution to this equation. So you can kind of use the calculator to determine which of those values is going to check. Here's another thing you could do. Do second and graph. And look at the values that you had. Like at 1, notice that the y and y2 are equal. So 1 is a solution. But if we look up at negative 4, we get 3 and which are not. That would tell us that doesn't work. So you have a couple ways that you could check on the calculator. Now let's do another example of this type, because this is a hard one, really. If you have the square root of 3x plus 4 is equal to a minus x, so we'd get squaring both sides. So that gives us 3x plus 4 is equal to, remember squaring this is like 8 minus x times itself. I'm going to get a trinomial, but you square the first is 64. Double the product, so that product is negative 8x, doubled is negative 16x, and square the last, which is always positive. So again, we have a quadratic equation to solve. We have to set it equal to 0. So to set it equal to 0, we can subtract 3x from both sides and subtract 4 from both sides. I'm just lining up those with my like terms on the right side. So I'm actually going to rewrite it in standard form with the variable term first. So that would be x squared, negative 19x, and then 64 minus 6 would be plus 60. So this time we have to look at what are the factors of 60 whose sum is 19. Okay. The factors of 60 whose sum is 19. And that is going to be 15 and 4. So, but the last sign being negative, that tells us, I'm sorry, the last sign being a positive there, or a sum, tells us we have the same sign here, both of them being negative. So when we set those equations or factors equal to 0, we get that x equal to positive 15, or x is equal to 4. So we have to check. And to check, we had the square of 3x plus 4 is equal to 8 minus x. So we have to plug in 15. We do 3 times 15 plus 4. Is that equal to 8 minus 15? Well, this is what? 3 times 15 is 45 plus 4 is 49, which is the square root of 49. Does that equal negative 7? No, because the square root of 49 is 7. So that does not make sense. So the 15 is not a solution. If we plug in 4, 3 times 4 plus 4, is that equal to 8 minus 4? Well, this is 12, 4, which is 16. The square root of 16 does equal 4. So the only solution is our 4. And again, we could see that graphically. We go to the calculator, and go back to tools, and clear this out. And in y1, we would enter the square root of 3x plus, close parentheses, and enter. And then we would enter 8 minus x. And if we graph where they intersect each other, notice that they only intersect, which is at this 4. Or again, we could look at the table, and if we go down to 4, we see at 4, the y1 and y2 values are equal, so it tells us 4 is a solution. Now, if we keep on going down to 15, we see that we get a contradiction because 7 does not equal negative 7. Okay? Problem I want to do for you is when you have the cube root of p minus 1 is equal to 2. So, let me change. And so we would get just p minus 1 is equal to 8, and add 1 to get 9. And then to check, is the cube root of 9 minus 1 equal to 2? Yes, because that is the cube root of 8, oops, which is 2. So the solution to that is 9. Okay, so if you have any problems with this, please contact me. Thank you.